I will give, well, I won't have time to give you all theorems of Goulart theory, but I would, at the end, I would indicate other theorems which I'm not going to prove. So today I'm starting with repeating what was last time. So we have extension. It's denoted K big over K small. This means that K small is contained in K big, and algebraic is finite dimensional. Dimension of big K over small k is finite. Okay, and we have done already much about algebraic extensions. Well, we proved that element of this finite dimensional extension is called algebraic. What we proved is that sum of the product of algebraic numbers is algebraic. And we also defined algebraically closed field as a field which doesn't have any non-trivial algebraic extensions. And I claimed that today I will reiterate it, that it exists, and also field C is algebraically closed. This is the main field which we work with, but there are other fields which are obtained as a field of fractions of polynomial functions on algebraic varieties, and they're not algebraically closed. Okay, and now also I used that polynomial ring is factorial. It admits prime decomposition. And if you have P of t irreducible, this is a polynomial in K of t. This happens if and only if the quotient polynomial ring by P is a field. This is something we have discussed last time. If you want to ask me questions about this, feel free. But you should know the proof now. And another important observation is that any field can be obtained by this is so if you do this is the same as you add t, which is a root of p. So this is called adding a root of p of t. Of course, the roots, if you consider them as elements in complex numbers, they are distinct. But from algebraic point of view, it doesn't matter which root you add. They're all the same. It's just because if you add the root, this means just you to take a polynomial and to take a quotient by the ideal. So from this point of view, all roots are have equal rights. Okay, and yeah, it's also called primitive. So definition, extension p k of t quotient by p. This is over small k. Is called primitive. And today I will prove that in characteristic 0, all extensions are primitive. This is one of the main purposes of today's lecture. But if it's not primitive, it doesn't matter that much, because you can just reiterate this. Okay, you added a root of some polynomial. So you start with a k, which contains k small. You take a root. If this take an element x. If this element primitive, meaning that it generates k, you are done. Otherwise, you obtain a smaller field, you add the root, So every extension is obtained as a chain, finite chain of primitive extensions. Questions, comments? I'm repeating what was last time. So if you have questions, you can ask. If not, doesn't matter. It was something you have already learned, as supposed to learn. Okay, and last time I was speaking about finite dimensional algebras. So A finite dimensional over K algebra, and finite dimensional over K. So dimension over K small of A is finite. Of course, and one of examples is a field finite extension. But it turns out that this is a theorem which we have proven, that if A has no nilpotence, finite dimensional, then dimension over K over A is finite, then A is direct sum of fields Ki, where each Ki is finite extension, is finite extension of K. And this theorem was proven. I'm not going to give its proof unless you really want me and ask some questions and so on. Yeah, it's called semi-simple if it has no nilpotence. No questions? Okay. Now we have an important, this really important number theory, bilinear symmetric form, trace form. Trace. So you have, suppose you have an algebra, A finite dimensional K algebra. Then each element in A gives you endomorphism of the finite dimensional space of A over K. It's a matrix. And you can take trace of A as an element in K. Now trace form takes A and B and maps them to trace over A of AB. Sometimes people write K here to indicate that you take value in small k. Because, of course, it really this form depends on the smaller field. Any questions? It is invariant form, and trivial observation that if trace of epsilon is not equal 0 for some epsilon, then trace is non-degenerate bilinear symmetric form. Indeed, for each A in your big field K, you take trace of A with a product, this bilinear symmetric form, with epsilon minus 1A, and this is the same as trace of A minus 1 epsilon. Trace of epsilon, this is non-zero. So this form is non-degenerate. Questions, comments? Okay. I'm going to use this to try to understand what happens if you take direct the tensor product of two fields. The idea is that the tensor product of two fields is always direct sum. It's semi-simple. Unfortunately, this is not true. This is not true because a tensor product of two fields might have nilpotence. And in that case, it is called non-separable, and it is separable otherwise. And it's actually easier and better from number theoretic point of view to define separable extensions from trace. So definition, extension called separable So it's finite extension, obviously, otherwise you won't have trace. Extension called separable if trace is non-zero. So last time I gave you this example. We can discuss it now. You have F, a P finite field. And then you take the field of rational functions. This is rational functions on this finite field. This is infinite field, but it's just quotients of two polynomials. And then you extend it with another field, which is F T. And then you add X. This is polynomial ring. And you take it's by a quotient by X power P is equal T. This polynomial is irreducible in this over this field, which is something you can prove yourself. It's not hard. But this is non-separable. Have you done this? No one? It's not hard. So let me do it now. Okay. What is the generators of? So this is fine dimensional space out of that. So what is its generators? So let's call this K big. K big is this bigger field. It's obtained by adding a root of a polynomial xp is equal t. So you just take a root, you add, so it's like f q p of t, and then you add a root, pth root of t. Right? But then, what is generators of this? Obviously, its dimension is p, and it's generated. So let's call this x. K generated by x, x squared, and so on, x power, well, p minus 1, because x power p is already t. So it's easy to see that this ring, up to this polynomial, it has basis of this, well, it's also unit. So this is the basis in this ring. Okay, we want to check that all elements in this basis have zero trace. How you do that? Well, you just you want to prove that all need to prove that all z in K big have trace over K small. This is K small of z is equal to 0. So let's look how what is the matrix of this. So 1. Z equal 1. The matrix is 1, 1, 1, 1, 1, 0, 0. This is p times. But p is equal to 0 because we in characteristic p. P equals 0, so trace of 1 is equal to 0. Now let's look at x, for instance. So matrix of x. Again, I use the basis which is written there. So matrix of x is 0 on diagonal. And then after diagonal we have 1, because x, this is the second element on base, it's x squared. X times x squared is x cubed, and so on. So you have, above diagonal you have units. And then if you multiply the p, the last element of the basis, by x, you'll obtain t. So in this corner, you have t. Trace is 0. And the same is for the rest. So if you have, so this is z equal x. If you have x squared, you just move it by 2, and you have two guys here. The trace is 0. This means that this extension is non-separable. And this is essentially the only example. OK. Now what we have is, yeah, you have Artinian algebra and non-degenerate bilinear trace form. In fact, it's not even trace. It's any form will work, but let's do with trace. The algebra is semi-simple, so theorem. Oh, yeah, it's better with trace. Sorry. Let's A over K, finite dimensional K algebra, trace non-degenerate. Then A is semi-simple. That is non-nilpotence. Okay, proof is one line, because if you have, say, epsilon in A, semi-simple, nilpotent. So nilpotent elements, they're upper diagonal with 0 on diagonal. They have 0 trace. But if you multiply nilpotent by something else, it remains nilpotent. So epsilon times x, nilpotent. This means that trace of epsilon x is equal to 0. And then trace of epsilon with something, whatever, is equal to 0. And this means that trace is degenerate. Trace is degenerate. Okay. So if we want, so what I'm aim is to prove that if you have, so what I need to prove, the following theorem, that if K over K small is non-separable, separable extension, then tensor product of K over K small is direct sum of fields. And the idea is to use trace. We just compute trace in that algebra and apply the theorem. This theorem says that semi-simple, of course, it's non-nilpotent, but what we proved last time is that if something is semi-simple, it's direct sum of fields. Questions, comments? No. So let's compute the trace. So to compute the trace, you should understand how what happens if you have two matrices in vectors over vector space. So you have matrix A1 and A2 from V to V. Or it's better not like that, but A1, or say A from V to V, and B from W to W. So this gives you a matrix formed by functorial properties of tensor product A tensor B from V times W to V times W. You just take any bivector here, like V times W, and map it to A of V times B of W. So do you have any idea what is the trace of this guy? This is an important but simple observation in linear algebra. So trace of A times B is equal, anyone? Trace of A, then good, trace of B. Precisely, thank you very much. So how you prove that? Well, it's not really hard. The point is that so suppose you have basis in V1 dot Vn in V, W1 dot Wm in W. We have our matrix A is Aij. This is the matrix for the linear operator A, and B is Bij. Then you have a basis Vi times Wj in V times W, right? This is how you write the basis in tensor product of two spaces. You take the first vector in one basis, second vector in another basis, multiply them. This gives you a basis in tensor product. Okay. And now you have like matrix with multi-indices. So you have A times B. You can take its index like I J. This is the first pair of indexes, and then I prime, J prime. So this is how it maps. It is you take this is A times B applied to Vi times Wj and projected along the rest of the basis to Vi prime W tensor Wj prime. So can you guess what is this entry here? No one? It's not really hard because you know what happens A of B of V1 times Vj. This is you take A applied to V1 and B applied to Wj. And then you project to here. This is you just apply the first project, apply the second, and project to here. So this is equal to I prime B I prime B J prime. So the matrix for A times B is A I prime B J prime. In other words, what happens is that this is a block matrix. So here you have, say, B with different coefficients. And the coefficient here will be A11. Here it will be A12, A13, and so on. Here we would have A21. Here we would have B A231, and so on. Or opposite order, I forgot how you write matrices. This, or you should write like 2, 1 here. Do you remember? Well, okay. This is the block form. So this is a product of two matrices. And now you can see the trace. So the first block add A11 times trace B. The second, add B A22, so it's A22 times trace B, and so on. So the whole thing, trace of this, is the same as trace of B times sum AII from I equal 1 to n, and this is the same as trace A times trace B. So the trace is multiplicative. And this is almost completely trivial. I didn't do anything which it should be obvious. If it's not obvious, I apologize. But who thinks it's obvious? Almost nobody, sorry. It should be. But maybe you should really do some exercises about tensor product, I don't know. Or just sit and think about matrices. Okay, now let's apply that to Artinian algebras. That's trivial corollary, so lemma. Well, you have R times, this, before I say that lemma, let me give you a definition. So you have a V with bilinear symmetric form G, W with bilinear G prime. Then you have a V times W, and you define a bilinear symmetric form G tensor G prime as follows. You take V times VW, you multiply it with V prime times W prime, G times G prime, right? And this would give you G of V, let's call this H. So this would give you G of V times V prime multiplied by G by H W prime. Okay, so what is good about this expression? It's clearly linear on all entrants. It's linear on V because V just occurs here once, and it is linear here. This is just independent on V. It's linear on all four entrants, so it's like 4 form. But any form which is linear on two entrants, on two multipliers in a tensor product, is actually extended to a linear form and tensor product. So this form is linear on both entries, here and here. So it's a bilinear form. It's bilinear by universal property. By universal property of tensor product. Well, it's bilinear by construction, but it's extended to a form on tensor product by its universal property. So if you have two, and of course, this is the same here. I mean, what will be the matrix of this bilinear symmetric form? It will be again block matrix of the same nature. You have the first block, which is the first form, times the first like A11 from the second form, and so on. Okay. Now the lemma. If you have R prime, finite dimensional algebras over K, and I would take the algebra R times R prime, we'll multiply that over K, and we're interested in trace. Trace in that algebra in is equal to trace in the first algebra. Let's denote the trace here will be denoted as G, and trace is denoted by H. So this is trace in R, this is trace in R prime, and then a trace in this algebra is equal to G times H. Why it is so? This is because if you have, so proof, suppose you have X inside R, Y inside R prime, then X times Y, X on R times R prime as X times Y in the sense of this definition. I mean, this is by construction. But we know what is its trace. Then trace of X times Y is product trace of X times trace of Y. This is what is in there. But again, this is bilinear on X and Y. So, and as we have done already several times, right? This means that for all linear combination of X times Xi times Yj, so this is Z is equal to sum Aij, trace of Z is equal to sum trace of Xi, trace of Yi, Aij. Right. Just by linearity of, so trace is linear on this and that. You have this, and then you extend this by bilinearity. Okay. And this gives you this. So you obtain, like, this is another definition of this form. So on the other hand, so now we can give a corollary. So corollary, you have K1 over K small and K2 over K small finite separable extensions. Then K1 times K2 over K small is semi-simple. This is a theorem. Because trace is not adjoint. So we are interested in trace form in K1 times K small of K2 is not degenerate, is a product of two non-degenerate forms. Non-degenerate as a product of two non-degenerate forms. Okay, and now it can be problematic because you don't know this result. Can you guess why the product of two non-degenerate forms is non-degenerate? Anyone? You did it for decomposable vectors. Decomposable, yeah. So you take x times y. These decomposable vectors. Not all vectors are decomposable. Precisely. Thanks. So look, unfortunately I erased this block matrix, but you can put it back. So we take tensor product of two bilinear symmetric forms, and we write it in block form. So I have this. So the first is A, is matrix of the G, AII, IJ, and BIJ matrix of H. So you have H block, and this is multiplied by A11. This is multiplied by A12, HA13. Here I have HA22, and so on. HA12. Now we are interested in determinant of this big matrix. So how you can prove that, and I claim that determinant of this matrix is equal to determinant of the first matrix, say G times determinant of H. So how you can prove such a result? Okay, let's change basis. The determinant is independent on the basis. We will change the basis in such a way that they are all diagonal and above, like upper triangular. Then the determinant is product of diagonal entries. And the product of diagonal entries, if these all guys are diagonal, is just product of the first and the second. This one of the another is to look at definition of determinant in terms of Grassmann algebra, and then this becomes completely clear without basis. But anyway, you know that every matrix can be translated to an upper triangular form by linear, right? So each matrix, if you add like pass to algebraic Cleurer, becomes upper triangle in a certain basis. You just take the first eigenvector, second eigenvector, and so on. Okay. So we obtained that this trace form is non-degenerate because it's a product of two non-degenerate forms, and this gives us semi-simplicity. Questions, comments? Okay, so I have a couple of examples for tensor products. So the most often we deal with an extension which has this form obtained by adding roots of a polynomial. So I have P of t inside K of t, irreducible. And we have an extension, K, which is just polynomial field, polynomial ring, sorry, quotient by P, by the ideal generated by P. This is a finite dimensional algebra over K. Let's multiply that by, so we can multiply K over K small by some other field, K prime, or just by K big, doesn't matter. And it is direct sum of fields. Of course, if I assume that this is separable. Say characteristic is 0 or something. We don't care about non-zero characteristic most of the time, so we can. So we're interested what are these fields. So let me give you an example where this works, when you can have an answer. So yeah, so obviously this will be equal to k prime of t quotient by p. This is just by definition. You change coefficients here, and you take the quotients by the same ideal, or by this result that if you have r quotient by I, tensor r prime is r prime quotient by r prime I. This is something we have proven about tensor product. So you just apply this result to this situation. So it turns out that if you are interested in what happens when you take tensor product of fields, you're just interested in this kind of quotients where p is no longer irreducible. I mean, it was irreducible in k small, but it's not really irreducible in k prime. So let me write a corollary, which is essentially Chinese remainders theorem, in fact. That if you have k prime, let's suppose it is extension of k small, p of t is irreducible polynomial. And suppose that p of t is a product of linear t minus ai in k prime of t. Then k prime times, so you have k is equal to k of t quotient by p. K prime times k over k small is equal to direct sum of, so let's assume here we have I equal 1 to n copies, so it will be n copies of k prime. So proof. I told you it's Chinese remainders theorem. So what you have is all polynomials k of k prime of t quotient by p, where p has this form. This is mapped onto direct sum of k of t quotient by t minus ai. And this is, of course, k prime. So what we need to prove is that this is an isomorphism, like of vector spaces, because this is clearly, I mean, you can take p and then you take an extra quotient by something which is divisible, which divides p. So this is clearly a homomorphism. You just take any polynomial and you just, it's up to p, but then you take it up to t minus ai, and p divides ai, so this is well defined. Okay, this is n-dimensional, this is n-dimensional over k prime. So what we need to show is to prove that it is an isomorphism. And now I'm proving just Chinese remainders theorem, which says that if you have like remainders by n, like t minus ai, and different, ai are all different, so it should be ai are different. It won't work, it's just wrong if they're not different, so they should be really different. This is important. But, of course, this is empty. If they're not different, this means that p and p prime have common divisor, but then p can't be reducible. So they're in characteristic 0, they're always different. In characteristic non-zero, this can be, the p prime can be 0, so this argument doesn't work. But we should, if characteristic is non-zero, you should assume that. Okay, so you have this map. Suppose something goes to 0. This means that it's a polynomial which goes to 0, which vanishes in all ai's. But then it is divisible by p. So nothing goes to 0. This is an isomorphism. Again, this Chinese remainder theorem, literally. So it's something that people usually learn, at least when they study for do Olympiad problems, they learn this. Okay. So this is an example where you just take tensor product of fields and you obtain this tensor product of fields explicitly. In fact, you have something stronger, namely if I mean the proof is the same, it's just slightly hard to assess, more hard to assess. So if you have P is product of Pi, P of t is product of Pi of t in K prime, then you take K prime over K small, K small of t quotient by P. This would give you direct sum. Here I have K prime of t quotient by Pi. So Pi irreducible. This again Chinese remainder theorem. Suppose again how you prove this. Okay, you have a map from here to here. Just the same map. You just take Pi are all I mean P divides Pi. So you can just when you take a polynomial you project it here. It's if it was divisible by P, it goes to 0. So it's well defined. And this is a homomorphism, just polynomial to polynomial. So how you prove that it is, say, injective? Okay, you have a polynomial which is divisible by Pi, but all Pi are coprime. Pi coprime. They don't have any positive degree divisors. And then if it is P is divisible by O pi prime, it's I mean it has like prime decomposition which divides P. And then it is if polynomial is divisible by all pi prime, this means that it is divisible by P. So this is really surjective and injective, and then it is surjective and isomorphism for the same dimensional reasons. Questions, comments? Okay, so this was example. What happens when you multiply things? Now let's do with algebraic closure. Algebraic closure is something we have discussed. I would indicate you how it is obtained. So you take some field which is not really algebraically closed, K. Okay, it's not algebraically closed. This means that you can extend it. So we replace K by K of t quotient by P, where P is a irreducible polynomial, positive degree. This is certain extension. Its dimension over K is precisely the degree of P. Okay, if it's algebraically closed, we're done. If it's not, we take a next extension, K of t quotient, this is K1. K1, we take K1 of t quotient by, let's P1, this will be P2. It's not algebraically closed. Okay, we do again. And then we take union of all of them all. If we're lucky, we arrive at algebraic closure. If we are not, we can do that again and again and apply Ntzor lemma. So this gives you the set of algebraic extensions is partly ordered. If you have like union of algebraic extension, it's algebraic. So this means that you have some maximal algebraic extension. As we discussed, the maximal algebraic extension is an extension which doesn't have any more algebraic extensions. And this is the same as algebraically closed. So the Ntzor lemma gives you existence of algebraic closures. Comments, questions? Okay, this last slide, and then we have a break. Or maybe not. let's have a break now. Like 5 minutes, but I'm slightly late, so really in 5 minutes we'll start again. It's 14:30. If you have questions, you can ask now, but generally you have 5-minute break. Diagram of fields. But we don't know what is these fields. It's very natural to expect that if you have an algebra, you do with the algebraic closure, then tensor product is algebraic closure. There is a proof, but I think I can give you a simpler proof. So suppose you have k over k small, find extension. And k small bar is algebraic closure. Then we take k big multiplied over k small with k bar. And I claim that this is direct sum of k bars. You can ignore what is written there because I think I can give you a simpler proof. Essentially the same, but simpler. So proof. I would take this is a direct sum of fields because it's finite dimensional over, I assume characteristic 0. Then for characteristic 0, all tensor product fields are again direct sum of fields. So we have k big tensor k small by k bar is equal to direct sum of certain fields. But all these fields contain, so this is finite dimensional over k bar. Because this finite dimensional over k, you multiply by k bar, this, as a vector space, this is just a product of, so as vector space, k is just k small power n, so k bar over k big over k small k bar. As a vector space is just k small bar power n because of that. So this, they are all this finite dimensional over k bar, so this is finite dimensional. But this algebraic closure, it doesn't have any non-trivial finite dimensional extension. Then this implies that k big I per k big I is equal to k bar because it's finite dimensional extension. Questions, comments? You have free time, you can peruse this proof. It's slightly different because I try to do more careful with separability, but we already proved that tensor product of fields is a direct sum of fields for characteristic 0, so it doesn't matter. Now I can prove this primitive element theorem. So theorem, if you have k big over k small, well, the proof works always for all separable extensions, but I don't want it to be, I would give it for characteristic 0. Then separable immediately, and then it's primitive. Always primitive. Let's discuss its proof. Okay, so suppose it's not primitive. But take any element which is not primitive. X inside K, non-primitive. Then you take K small of X inside K. This is a subfield. I will prove that there are only finitely many codimension of this K of X in K big, finite, but positive. It's a subspace, a vector subspace in there. So it's, yeah, better to say codimension over K, and then you take this inside K big. I prove that there are finitely many subfields. Then you take K big, you remove this Ki, finitely many, and the rest is primitive elements, right? So I'm not proven that yet. I will prove it soon. But suppose that this is true. Then we have finitely, in a big vector space, you remove finitely many subspaces of positive codimension. Then I claim that general element is not in these subspaces. This is a simple problem of linear algebra. For R, for instance, you can prove it by saying, okay, or C, by saying, okay, they have measure 0. It's a measure 0 subspaces, and the complement is dense and open. But generally, it's a nice question of linear algebra. So you take a vector space over infinite field, and you remove finitely many subspaces. You are going to prove that the complement is non-empty. Can you do that? Let me write it. So exercise. You have V is K power N. You have W1 Wm inside V. Positive codimension subspaces. Then V without the union of Wi is non-empty. Anyone? Okay. The idea is to use induction. So you have when let's forget that linear spaces. Let's do with affine spaces, slightly easier. You can do with linear, doesn't matter, but it's easier to write pictures. So if you have, suppose that V is two-dimensional and W is one-dimensional. You have these lots of lines. Then you intersect them with a line which is intersects each of these lines transversally. So it's not, it doesn't lie in any of these lines. Using induction, this is possible to do, because you just take the corresponding projective space, so you have a line and finitely many points on it. Of course, the complement to finitely many points which are intersections. If you remove finitely many points, your field is infinite. So this gives you this blue line contains points which don't belong to these white lines. And then use induction. So this is one of the methods you can prove this result. Another method is, okay, let's just take closure, algebraic closure. This would give you C. or R, and then your field will be dense, well, you just prove it over C and R. And then you say that, okay, the set of points which are over in our field is dense in the set of all points, because all subfields are dense in R already. And for R, we can do that using analysis. Anyway, I'm leaving this to you as an exercise because I thought you know how to do it. And let's proceed. So this is left as an exercise. Now let's prove the primitive element theorem. So what we need to show is that there are finitely many subalgebras in this tensor. There are finitely many intermediate fields. So if you have, so this is lemma. If you have K over K small, contains K contains only finitely many intermediate fields. K containing K1 containing K small. Then you take element which is not in this intermediate fields. You use this result, and you obtain that indeed general element is not in these subfields. So we need to prove it. Okay, I'm doing something easier. So I do sublemma, say. It's lemma here in the top. If you have a direct sum of k's, just k direct sum of fields, for instance, but they are all isomorphic to k. So you have k power I, n, has only finitely many different K subalgebras. It turns out that all subalgebras are just, you take some subset in this direct sum, and this gives you some subset, gives you some direct sum of fields, several copies of K in this direct sum, and this is only subalgebras which are possible. There are no other subalgebras in this direct sum. So the proof, okay, we know that every algebra without nilpotence is direct sum of fields. So every algebra is generated by its idempotent, which is unit in this subalgebra. So there are as many idempotents as subalgebras. Okay, so we just need to count to prove that there are finitely many idempotents. Idempotent is an element which is squared to itself. So you have I inside this K power n direct sum. Idempotent, A squared is equal A, idempotent. And then we have also n idempotent which correspond to the summons. E1 dot En inside K power n generators of K. On each place you have a certain idempotent. Then a sum of EI, A square, A, is also, well, it's equal, obviously it's equal to A, but then EI, A is idempotent, which is contained in K EI, which is just K. It's one of the components in the direct sum. Okay, in the field there are only two idempotencies, 0 or 1. So this is equal either to 0 or to EI. Then A is just sum of certain EI, IK from K inside certain subset, sigma. Sorry, IK. Okay, finally many, right? Just to take subsets, there are no other. Okay, good. Now we want to prove this. This lemma. Oh, sorry. We want to prove that there are finally many subsets, subalgebras. Let's prove that. So we have K big contained in K small. We have Ki inside K1, inside K big, this inside K small. Okay, let's multiply everything by K bar. So we apply this functor of tensor multiplication by algebraic closure. This gives you K bar contained in K1 times K bar, and this is over K small. And this contained in K big times K bar over K small. And as we proved, this is K bar power n. And this is an intermediate subalgebra. Then we know that there are finally many. Okay, we are done. This is the proof. So again, how you prove that every every field contains a primitive element. First you count all subfields. There are finally many subfields, and they all have positive codimension. Then you use this exercise that if you have a vector space, you remove some finally many positive codimension vector spaces, it remains the rest is non-empty. As long as your field is infinite, of course. Okay, so you take, and then there are finally many subalgebras. You just, proper subalgebras, you remove them all. The rest is primitive elements. That's all. Okay, I'm done for today's main part, but let me give you some survey of Galois theory, which you will definitely need to learn at some point, and we're almost done in the sense that I have introduced pretty much everything you need for Galois theory to state the main result. I'm not going to prove it, but you can do it as an exercise. It's possible to do it without doing much. Okay, so I start with the definition of Galois extension. There are several ones, and they are given here as exercises. But the most convenient one is, again, with tensor product. So definition. Have finite extension. K big over K small, finite extension. And then we know that, well, we assume it's it will be a posteriori separable. So we take K big over K small with K big. We know that this direct sum of fields, if it's separable at least. But if this is just direct sum of certain copies of K, not the bigger field, but K itself, then this extension is called Galois extension. Okay, and then now I have a couple of exercises which give alternative definitions of different characterizations. Well, this is just the second exercise is just existence, and the first is alternative characterization. So exercise 1. Suppose you have primitive extension K over K small, primitive extension. Primitive means that k big is polynomials quotient by certain irreducible polynomial. Then k big is Galois extension if and only if P is reducible, P of T is product of linear in K big of T. This is more or less we have done already, because we have discussed this thing with the when I spoke about Chinese remainder theorem. So if this is, if k big, so the standard product is k big over T quotient by T. So k times k small times k is k big over T quotient by P. And if P is completely reducible, it's a product of linear multipliers, then this is the sum of k, and converse is also true. It's easy. This is one. This is a sort of characterization of Galois extensions in terms of the polynomials. So if this is what happens if you are lucky. You have a primitive, you pick an element that is primitive, and then it should have, its polynomial should have all roots present. But then so what happens if not? This is second exercise. Suppose that again k big is P of T, it's k small of T quotient by P. Then of course P in K big, P is a product of some Pi, which are irreducible. This is a reducible decomposition for P in the bigger field. Okay, they all have some roots. I mean, in some bigger extensions, so we can add roots of Pi. Then you have a bigger field, which it's possible that Pi would decompose, but not onto linear multipliers, but some positive dimensional multipliers. Do again. Decomposed Pi, add roots. In the end, we obtain extension K1 over K with P of T is a product of P Ti minus Ai. So we added all roots. Then K1 is Galois. So Galois extensions always exist. And again, the proof is by looking at this right here. Okay. Now, yeah, Galois group. How much time do I have? Good. Generally speaking, the automorphism of the bigger over smaller field over small could be anything, could be empty. The typical example when it is empty is automorphisms of R over of R, real numbers, over Q. This is really big. I mean, R is huge, it's continuous, and Q is small. But still there are no automorphisms. Why? Because an element in R is positive if and only if it has square root. This means that all automorphisms preserve positive elements. They preserve order. But it's easy to see using Dedekind whatever, how it is called, sections. Dedekind sections, right? Well, that any automorphism of R which preserves order is in fact identity. So this can be very small. But the good thing about Galois extensions is that they have lots of automorphisms. In fact, so this characterization of Galois exercise, which is less trivial than the previous exercises, that k over k small is Galois if and only if the automorphism group is sufficiently big, in particular that if you take k and take invariant under G, where G is automorphisms of k big over k small, then this is k small. So each element which is not k small can be moved somewhere by automorphisms. For instance, if you have C, then each rational element can be moved somewhere by an automorphism. There are lots of automorphisms of C because it's obviously Galois. Well, it's like limit of Galois extensions because Galois in our terminology is finite. But anyway, okay. Now the main theorem of Galois theory, yeah, it's called Galois group. It's called Galois group. Gal of k over k small. Now the main theorem of Galois theory is the following. So you have a bijection between subfields and subgroups. So you have here, you have k over k small Galois. So here you have so the Galois group of k small over k big over k small. And you can have subgroups H. And here you have k, you can have subfields. And let's consider subfield which is invariance of H action on this. This is one-to-one correspondence between subfields, so subgroups, are one-to-one correspondence with subfields. There are as many subgroups as there are subfields. So in fact, what happens is that there's a categorical equivalence. With each group, you can associate a certain category, which is called, we call them Galois category of representations. And with each field, you can associate a category which is category of extensions. And then you have an equivalence. Yeah, and also you can characterize Galois extensions here. So H is normal if and only if this is Galois. So H normal if and only if KH is Galois. This is actually how people first invented groups and normal subgroups. It was Jordan who found that in unpublished manuscripts of Galois. There's one more. Okay, this exercise, right. So now I want to give you an example, and then I am done. Let me give you an example. Yeah. This is again something you can, in theory, you can do. And it would take probably one lecture to explain everything in very proper details, but you can do it without yourself. So, exercise. You have Q, which is p power n. Prove that there exists a finite field, which is denoted FQ, with Q elements. And containing Fp, which is Z by P, just a standard field of P elements. And then Fq over Fp is Galois. And the Galois group is cyclic and generated by Frobenius automorphism, which is automorphism of Fq to itself. Very simple, like Frobenius of A is A power P. It's sort of easy to see that this automorphism because, I mean, it's clearly multiplicative, and to see that it is additive, you just remember binomial coefficients. And all binomial coefficients are divisible by P, so they are 0. So this means that Frobenius of A plus B is A power P plus B power P plus some other summands which are all divisible by P, so they are vanished. So Frobenius is OK. Now I'm really done, and thank you very much. And you will have on your monitoring session some test again, I think. And unless you don't like it, and you will let me know. And next time we shall go to things like Zariski topology, birational maps, and so on. So no longer Galois theory.